Okay, I'm recording this is the last thing that we're going to do with the Excel file. And we have to prepare, the goal of this lesson is to prepare a table like this. We need these 7 rows, total 15, the windows, the total losses, to the rest of the envelope, the walls, roof, window, whatever, the ventilation. Then we need the heating and cooling demand. I will explain what this is later. The COP. COP stands for coefficient of performance. I'll explain what the coefficient of performance is. And then here we have this row, heating and cooling demand, divided by COP. Those are the electric appliances. This is the number that comes from this table. You have to make a list of all the electric appliances that you have, the monthly consumption, roughly, and then you have to add all this up. And this is the number that we have here. Okay, so all the rows, all the months have the same consumption. And finally, we have the AC system from PV watts. Okay, so let's do it. We have this table, and I'm going to do it again from scratch. And I think I'm going to make those rows. What is the row height is 15. So I'm going to make this 50 so that we can see the numbers better. Okay. So what's the first row? The first row, we have the months from January to December. The second row, it's the number of days that we have on each month. 31 days in January, 28, 31, 30. Okay, so that's easy. Now, here we have the solar gains. So what are those solar gains? It has to be the same number that we have in this table in BTUs, but we have to turn this into kilowatt hours. So those solar gains, remember that now we are using kilowatt hours. Okay, so if last day we calculated this number as the solar gain, but that was in BTU, now we have to turn this into kilowatt hours. What's the conversion factor between BTU to kilowatt hour? It's this weird 0.00029, whatever. So I copy this, copy. So this cell is the same cell I have here in BTUs times this number 0.000, whatever. I click OK, and this is, I'm going to make this number, this font bigger. Okay, so this number is the same number as this one, but converted to kilowatt hours. And then I only have to drag it all the way. And there you go. When those things appear, it's because the column is too narrow. And if we increase the width of the column, then we have a valid number. Okay, so here we have solar gains in kilowatt hours. The same number we have here, it's that cell. Multiplied by this conversion factor 0.0002930. Second column. The second column is the heating, the total losses in kilowatt hours too. So the second column is if we use the same color code, that's very easy because we have this in BTU and we have this in kilowatt hours. So this one should be the blue cell in BTUs times the same conversion factor, 0.000290. And let's make it bigger. I made a mistake. This is the blue times this. Yep. And now drag it until December. So those are total losses and units kilowatt hours. Yep. So here, the first two rows, it's the solar gains, the same value as this one, but kilowatt hours. And the second row is the same value converted to kilowatt hours. What's the next one? It's heating or cooling demand. Okay, so what do we have to do now? If I have heat losses and I have heat gains, what I need is the difference between the losses minus the gains. Okay, so since I have a negative number here, because I in the previous table, I just to as a criteria, I selected that the positive numbers are losses, the negative numbers are gains. Okay, so what do we need now? We need to add these two rows up. So that equals gains and losses. Okay. And I'm going to make it bigger, the font size. And I'm going to drag this all the way here. So this is the heating. And cooling. And the units are kilowatt hours. Again. Like this. Okay, but there's something that I don't like here because I have positive numbers and I have negative numbers. Usually I will have a positive number in winter, negative number in summer. Here I have negative numbers all year long because again, I'm not doing an actual building with the real data. So I'm just typing numbers there. But usually we'll have positive numbers in winter, negative numbers in summer. Negative means cooling. But when it comes to electricity, heating or cooling, we have to supply electricity. So there is no positive or negative. When I have the total figure, I need to provide electric current, electricity, to supply the energy that I need, either for heating or for cooling. Okay, so in this table, positive or negative values don't make sense. Don't make sense. So how can I do that? If I add this row and this row, and I can have either positive or negative values, how can I get always a positive value for the electricity supply? Well, there are different options in Excel. So I'm going to show you another feature of Excel, another function that is very useful. And it's a logical function. Okay, so I like this one because we have to think. We have to think as Aristotle thought 2,500 years ago in the classic Greece. So he was the one who invented, or he invented. logic. Okay, so this is something that we do every day. Okay, so if I have this and then I have that, then the result is this. So those are logical reason. So those are logical statements, and we do every day, but sometimes we forget that we're doing it. Okay, so how does a logical statement work here? Let's use the function if. Okay, so there's a function by the name of if. Good. And now we have the logical test. Okay, so what is my logical test? I want to have a positive number here, always. Okay, and so if I add this and this, if I add up these two rows, I can have a value that can be either positive or negative. Okay, so my logical starts like this. If I open this parenthesis, if this number plus this number, what means that it's positive? It means that it's more than 0. Okay, so that's the logical statement. This number plus this number, it's positive, more than 0. Then, what if the value is true? If the value is true, it's this number plus this number. And what if it's false? So if it's not positive, that means that it's negative. Then I have to turn this value into a positive value. How can I do that? I multiply this by -1. So it's this plus this multiplied by -1. I click OK, and I do have a positive value here. And if I drag this, all these values will be positive. Look at this. This is negative 7,000. Now it's positive 7,000. This was negative 9,400. Now it's positive 9,400. And if I drag this, all these values are positive. So you see this is about thinking. Sometimes we have our head and we need our head we need to use our head for something different than wearing a little hair. I don't know what that was. So we have to think. So that's a logical thinking. What do I want? I want a positive value. Okay, so I have a statement. If this is more than 0, if it's positive, then I type the same value. If it's negative, I have to multiply times -1. And now, with this logical statement, I have the positive value of the heating and cooling. Because I'm working with electricity. So electricity, we have this positive, negative, just a criteria. Losses, positive, gains, negative. But then we have to supply the energy. So we don't supply a negative electricity or positive electricity. We supply electricity. So we need a positive value there. Okay, so this is the only challenge that we have in this table. We need this if function, which is very useful because sometimes we need a value if something happens, a different value if that doesn't happen. So that's the heating and cooling. Now I have another thing to explain here. It's the COP. What is the COP? Let's find out. COP stands for in engineering. COP stands for coefficient of performance. Okay, and here we have a definition. COP is defined as a relationship between the power in kilowatts that is drawn out of the heat pump as a cooling or heat and the power that is supplied to the compressor. What does it mean? Okay, that's the meaning of COP, coefficient of performance. So the coefficient of performance, we are talking about a heat pump. We will talk about this in systems because next year, by this time next year, you will be taking systems if you are in architecture. But even if you are not taking systems, this concept of the coefficient of performance is very important because now we tend to use electricity for heating and cooling. We can do two different things for heating. We can burn fuel, and by burning fuel, we release CO2, or we can use electricity. If we use electricity, we don't burn fuel, and we can have electricity out of renewable energies. So this is what we are doing in our building. We are not burning fuels, we are using electricity, and that electricity comes from the PV array that we have designed. If we use electricity that comes from a thermal plant that burns fuel, using electricity doesn't provide us with any advantage from the sustainability point of view. But if all the electricity that we are producing comes from renewable sources, then what we are going to explain now, it makes sense. If we burn coal to produce electricity, which is, by the way, what 80% of our electricity comes from burning fuels. Okay. But if in the future we figure out how to produce electricity with renewable sources, that will work quite well. So let's assume that our electricity is coming from renewable sources. Our electricity in our building comes from the PV array. And then we have thermal losses. Okay, so everything that we have calculated as BTUs are thermal losses through the windows, because of the ventilation, through the walls, roofs. So all that means BTU means that it's thermal. And now we have to turn this thermal energy into electricity. So that's why we need this concept of the coefficient of performance. The coefficient of performance is the relationship between the thermal energy that we need and the electricity that we use. Okay, so in electrical systems, in heat pumps, we have this concept. So if we have cooling in our homes or in our buildings, we need electricity. We can cool down a building by burning things. Okay, so if you want to cool down the air, you don't burn. Doesn't make sense. We need electricity. If we want to heat up something, we can burn fuel and then we heat up whatever. We can heat up air, water, or whatever. But let's assume that we don't want to burn anything on site. Okay, so you will have a nice building there on campus, and we don't want the chimney expelling gases that comes from the combustion of fuels. We don't want that. So we are going to use an electrical system. So if we use an electrical system, we need this coefficient of performance, and that's the difference between the thermal and the electricity. Or it's the relationship, not the difference, but the relationship between the thermal energy that we want to generate and the electricity that we want to consume. Okay, so the COP first is always positive. Okay, so we don't have negative values of COP. It's always positive. Second, it ranges from 0 to infinity. Okay, so 0 is the worst. So if we have a 0 COP, means that well, basically we have a device that turns everything into electricity. Okay, that we need a lot of thermal and or we need a lot of electricity to generate the thermal loads that we need. So that would be a disaster. Okay, so if we had a system with a COP 0, it's terrible. But if we had a COP of infinity, that would be great, because that means that we need 0. If we divide something by 0, then the result is the infinity of infinity. So that would be an optimum device. We don't have this on the Earth's surface. Do we have it in a different planet? I don't know, and I don't care. But we are far from getting to this infinity COP. So COP usually ranges from 2 to 6. Okay, so if we find a device with a COP of 2, okay, not very good. So the best available device that we have to provide heating or cooling to the buildings now, it's around 6. It's growing. Okay, so probably in 20 years we will have values of 7, 8, maybe, I don't know. And how can we find that? If we go to okay, if we go to specifications of heat pumps, I'm going to the Daikin website. Daikin is a German brand, and here if they are selling this kind of things, okay. So look at this. Here we have information about different ratios. We have the seasonal energy efficiency ratio, I like COP. Okay, so those are, it's always the same concept, but with different units. But I like the COP because we are dividing kilowatts by kilowatts. So this COP is 4.56. Okay, so imagine that we use this device, this Daikin, this heat pump, okay, and the COP is 4.56. So that means that if we have, or if we need if we need 1,000 kilowatts of thermal energy, if our coefficient of performance is 4.6, what is the amount of electricity that we need? The electric power would be 1,000 divided by 4.6, and that equals what? 1,000 divided by 4.6. Okay, so that's the idea. We have calculated thermal loads, and now we are going to supply this energy with electricity. So we need a device with a coefficient of performance. The higher, the better. If this coefficient of performance, I told you that it ranges from 2 to 6. 2 is very bad. 6 is optimum. 4.6, quite good. So what's the actual electricity that we need? It's the thermal load that we have calculated divided by the coefficient of performance. Okay, so here we have to type coefficient of performance, and it's different. So the coefficient of performance probably it's different in winter and in summer, but just to make things simple, we can assume that the coefficient of performance that we're going to use, it's always the same, 4.6. Okay, so this coefficient of performance, it's always 4.6. And now what do I have to do? I have to divide the heating or cooling demand, the positive one that I have calculated in this cell, I have to divide it by the coefficient of performance. So this is this cell divided by the coefficient of performance. There you go, we have this number. So I do this, and this is heating and cooling. Divided by the COP in kilowatt hours. Okay, so this row is heating and cooling divided by COP. Are we done? No, not yet, because here we need the value of the electric appliances. So what's the value of this electric appliances? This is what I have calculated here in this table. Okay, so in this table, in this case, with all these appliances, I have 555 kilowatt hours per month. So I have to type here 555, make it bigger, and then drag it here. And finally, what do I have to type here? This is the AC from PV watts. And these units are also kilowatt hours. Okay. So what's that? It's the result of my, I'm going to just work with this example. If the roof area is, let's say, 4,000 square feet, if the area of one panel, so the number of panels would be 4,000. The area of one panel, how much is the area of one panel? Yeah, say 15. 15.
Let's go. Let's go.
15. So how many panels do we have here? 4,000 divided by 15. Divided by 15. Okay, so I can have 26.6 panels. So let's say 260. So around 260 panels. And what's the DC system size? The number of panels, 260 times 185 watts divided by 1,000. So that is 260 times 185 divided by 1,000. It's 48. So this is 48 kilowatts. So I have to go to PV watts. In New Hampshire, DC system size is this value, 48. Now, if my tilt, if it's horizontal, let's say that the tilt is 0, and then the azimuth is that, then I go to these values, and I have to copy this chart here. Okay, and then I have to type this AC energy that I get from every for each month. So in January, okay, I have to type 2,397. This is 3,169. 4,866, 5,9, 4, 5,932, 6,108, 6,573, 5,603. Okay. So we are done. What have we done here? We have the what we need for heating and cooling every month. What we need from the electric appliances, and this is what we produce. Okay, so if we were analyzing this building, I told you that it's not an actual building, so I have typed the values here, but I don't know if it's the values might not be correct. But if we have this analysis, this is the what is the energy that we need to supply? We need to supply 366 for heating and 555 for the appliances. So this is what my building consumes in January. How much am I producing with my PV array? 2,300. So I'm producing more than I need. Okay, so probably I need to sell that excess of energy to the grid. Are there months in which it's negative? Yes, here, for example, in July, I need this 7,190 for cooling. I need to consume this for electricity, the same with the PV, the washing machine, and all that stuff. And I'm producing less. Okay, so that month, I have to take, or I have to buy electricity from the grid. But those values are quite good. Okay, so usually, especially in winter, in January, February, November, December, your consumption would be much higher than your production. This is what should happen. Okay, but in this case, I don't know. I have typed here values that probably are not reasonable. I'm going to change values here so that, okay. So this is something that you usually have, okay? So we have like 60,000 of heating needs, 500 for the appliances, and I produce 2,000. Yeah, so that's reasonable. But with this table, we can know how far we are from the zero energy building. if we want to know how far we are from that goal, I can always add this here. And this here. And this there. And finally, I have to add this up equals this plus this. Okay, if I compare these two values, this is the electric needs. And this is the electric supply. Okay, so in this case, I supply with my PV array, I supply more electricity than I need. So yes, I am in a zero energy building. Okay, so I have to add up the energy needs from the heating and cooling and from the appliances. So that's the sum of these two values. And then this is the sum of all the months that we have, because I have to assess the zero energy building throughout the year. It's not month by month or day by day. So I have to do this throughout the year because in this building in winter, I need electricity, okay, because I consume more than 6,000 and I only produce 1,600. So in December, I would need electricity. But apparently in summer, I produce much more electricity that I consume. I produce 6,000 and I'm consuming around 2,000. Okay, so the balance throughout the year is positive. So this is a zero energy building.